Hello, thank you so much for watching our video. My name is Josh Drost.
And I am Arric McLauchlan. We will be talking to you today about three-dimensional analysis, finite element analysis of a composite block. There are many types of composite materials that are commercially available on the market today. A large portion of these materials fall under the category of fiber-reinforced composites, though other types of composite materials do exist. A fiber-reinforced composite material consists of a strong fiber filament that is usually a material with a high Young's modulus, a high density, and a high cost associated with it. This is generally surrounded by a different material known as the matrix. The matrix material is generally more pliable and less dense. The fiber is the main support mechanism that takes the bulk of the applied load, while the matrix is used to distribute the load to the fibers, as well as hold the fibers together. Composite materials are being used in a variety of industries today. Due to their lightweight nature, and the aerospace industry relies heavily on composite materials for use in aircrafts. With an increasing demand for efficient vehicles, the automotive industry has been adapting composite materials for the purpose of producing lighter and more efficient vehicles. The construction industry also uses many composites. Can you think of an application in this field? Foundations are commonly steel-reinforced concrete. This is a form of composite material. Even the sporting industry has been utilizing composite materials for lightweight golf shafts and protective equipment. A lamina is a single layer of a composite material. It is often an orthotropic material, meaning it has different properties in different directions. When these laminas are stacked on top of each other, they form what is called a laminate. A laminate composed of different laminas oriented in different directions can have some very interesting material behaviors. Not only are composite materials anisotropic, but they are also heterogeneous. This means that the material properties are different in different sections of the material. This has severe implications that cause exact analysis solutions to be next to impossible to formulate. Many heuristics and meta-heuristics have been proposed. However, these are all approximations based on observations.
An alternative to using the analytical technique is to use the finite element method that we've learned in class to analyze the behavior of a composite material. This allows us to treat each section of the composite independently, thus eliminating the heterogeneity and anisotropy of the material. The actual analysis of a three-dimensional fiber-reinforced composite is very similar to the two-dimensional homework we did for homework 4. There are some changes, such as the elasticity matrix is now a 6x6 instead of a 3x3, but the strong form looks very similar. Shown to the right on this slide is a picture of the mesh we're using. There are 3 circles in this which show the fibers, and the rest of it is our matrix. We're using a hexahedral mesh, which means they are cubic shaped. Other options are tetrahedral, but those run into locking issues similar to what we talked about in class. Another big change from 2 dimensions is that now there are twice as many shape functions, and that the master element is now a 3-dimensional cube rather than a 2D square. We are using a composite material, so there's a different elasticity matrix for each element based on whether it's in the fiber or the matrix. This also means that our F matrix is now a 3x3 rather than a 2x2, and that the B matrix is a 6x24 rather than a 3x8. However, formulation of the K matrix is exactly the same as it was previously, just with another dimension involved. It is now much longer, but still rather the same. In the next slides, we're going to show you some animations of our analysis. Here you can see an example of a single fiber element being stretched along the direction of its fiber. As you can see, at the end of the stretch, the stress in the fiber is less than the stress in the matrix. On this slide, you can see the image of the fully deformed element as it's been deformed along the direction of the fiber. So in conclusion, three-dimensional finite element is very similar to two dimensions. There are more shape functions. All of our matrices tend to be about twice as big. But besides that, a lot of the setup is exactly the same. This also means that we can use finite element to test composite material responses to deformations fairly easily, whereas the analytical solutions are much more difficult. Thank you so very much for your time.